Hi, I'm Melissa.
Juggy.
We will be teaching you about circular motion. It is when an object travels around in a circular path. Centripetal force and centripetal acceleration are both center-seeking quantities, while the velocity wants to go straight and not in a circular path.
Here's an experiment that will show you how to find the centripetal force, velocity, and centripetal acceleration. Now we're going to do an experiment to show you how circular motion works. In this experiment, we're going to show you how to find the velocity, centripetal acceleration, and centripetal force. In order to find velocity, you need to find the radius of the object and the period.
The period is the amount of time it takes for the object to make one complete cycle. Now we will be measuring the radius of the object in inches, and then later converting it to meters. It's out to be
24 inches.
Okay. In order to get inches to meters, you have to do conversion factors. Okay. There's 1 inch in 2.54 centimeters, and by doing it with this proportion, the inches cancel out, which leaves you with centimeters. Then there is 0.01 meters in 1 centimeter, and by doing it this way, the centimeters cancel out, which leaves you with meters, and then you just have to multiply the fractions in order to get your answer in meters. And by doing this, we found out that 24 inches equals 0.6096 meters. Now we will be measuring the mass of the object. Turns out to be 198 grams.
Now we'll be converting 198 grams into kilograms by using a conversion factor.
1 kilogram equals 1,000 grams. So by doing that, you will cancel off grams. Then you will divide 198 by 1,000, which will give you an answer of 0.198 kilograms. Now we'll be doing an experiment to show you how circular motion works. We'll be calculating the period by counting how many cycles Lindsay completes in 10 seconds.
Ready? Go. Stop.
14. Lindsay completed 14 cycles in 10 seconds. Now we're going to be calculating how many cycles Lindsay does in 15 seconds.
Ready? Go. Stop.
Lindsay completed 20 cycles in 15 seconds.
Now we'll be timing how many cycles Jackie completes in 10 seconds.
Wait. Start going and I'll tell you when. And you're off. Wait, yeah. And stop. 13.
Jackie completed 13 cycles in 10 seconds. Now we're going to measure how many cycles Jackie completes in 15 seconds.
And go. Stop.
21. Jackie completed 21 cycles in 15 seconds.
I got it.
Period is the amount of seconds in one cycle.
In order to find period, we will divide seconds by cycles.
To find the period, you divide 10 seconds into 14 cycles.
And you get 0.70 seconds per cycle. In 15 seconds, I completed 20 cycles.
To find the period, you divide 15 seconds into 20 cycles.
And you get 0.75 seconds per cycle. In 10 seconds, I completed 13 cycles.
To find the period, you divide 10 seconds into 13 cycles.
And by doing so, you get 0.77 seconds per cycle.
To find the period, you divide 15 seconds into 21 cycles.
And doing that, you get 0.71 seconds.
To find velocity, use this equation. Velocity equals 2 pi r divided by time. To find Lindsay's velocity in 10 seconds, you multiply 2 pi and 0.6096 meters, then divide that by 0.7 seconds, and you get 5.5 meters per second. Now to find Lindsay's velocity in 15 seconds, you multiply 2 pi and 0.6096 meters, then divide that by 0.75 seconds, and the result is 5.1 meters per second.
To find Jackie's velocity in 10 seconds, you will multiply 2 pi and 0.6096 meters, then divide by 0.77 seconds, and your answer will be 5.0 meters per second. To find Jackie's velocity in 15 seconds, you multiply 2 pi and 0.6096 meters, and then you divide by 0.71 seconds, and your answer is 5.4 meters per second. Centripetal acceleration is the acceleration that holds an object in its circular path. To find centripetal acceleration, you square the velocity and then divide by the radius. To find Lindsay's centripetal acceleration in 10 seconds, we take her velocity, 5.5 meters per second, then we square it, and then we divide that by the radius, which was 0.06096 meters. Lindsay's centripetal acceleration was 49.6 meters per second squared. For 15 seconds. Now we're going to find Lindsay's centripetal acceleration for 15 seconds. We take her velocity, 5.1 meters per second, and square it. And then we divide that by the radius, which is 0.6096 meters. And Lindsay's centripetal acceleration was 42.7 meters per second squared.
To find Jackie's centripetal acceleration in 10 seconds, you square the velocity, which is 5 meters per second, and divide that by the radius. You get the result of 41 meters per second squared. To find Jackie's centripetal acceleration in 15 seconds, you square the velocity, which is 5.4 meters per second, then divide by the radius of 0.6096 meters. Then you would get the result, 47.8 meters per second squared.
Centripetal force is the force that acts toward the center of the circular path. To find Lindsay's centripetal force in her 10-second interval, you multiply the mass, which is 0.198 kilograms, by her acceleration, which was 49.6 meters per second squared. Her centripetal force came out to be 9.8 newtons. To find Lindsay's centripetal force in 15 seconds, you multiply the mass, which is 0.198 kilograms, by her acceleration, which was 42.7 meters per second squared. This came out to be 8.5 newtons. To find Jackie's centripetal force for 10 seconds, you multiply 0.198 kilograms by 41 meters per second squared, and your force comes out to be 8.1 newtons. To find Jackie's centripetal force for 15 seconds, you multiply 0.198 kilograms by 47.8 meters per second squared, and it comes out to be 9.5 newtons.
Centripetal force keeps the object moving in a circular path, and if the force is broken, the object wants to go straight. Circular motion shows Newton's second law, which says that force causes mass to accelerate. And if the centripetal force is the same as the net force, because the centripetal force causes the mass to accelerate in a circular path.
Now Lindsay and Dima will be doing a softball pitch that shows that the ball does not want to go in the circular path and it wants to go straight.
Ready?
Yeah. This shows how the centripetal force wants to keep the object in the circular path until the object is released and then the object goes into a straight path. Here are two other examples of how circular motion works.
Ready? Go this way. Oh God!
Oh my gosh.
Go. Grab a trunk.
Let go. This experiment shows both circular motion and Newton's third law. When released, Lindsay and Demo both fall backwards because Newton's third law states that the two objects exert equal forces on each other in opposite directions. That was a good one! As the hula hoop goes around Jackie's arm, the force keeps the hula hoop in place. And once it's released, the hula hoop travels in a straight path like the velocity wants it to.
Circular motion is part of everyone's daily lives, whether you're driving a car, playing sports, or just hanging out with your friends.
Yeah, bye! Oh, what's up, buddies? Oh my god, you can see my birthmark on my chin. Centripetal force, celebration, is part of the course, it's rolling the nation. Get rid of that.
Oh, best?
This is Demo being a retard.
Wait, this is nice. Oh, that's lovely. Boom! Roasted. The end.